let's finish up chapter 28, which is the last little bits we're going to have before the midterm. Next week we're starting chapter 29, but that's not going to be on the midterm, right? So make sure you're getting all this material. And I posted all the lecture notes for chapter 25, 4, 6, and I'm going to post the 28 also today. That way you have all my little scribbles on Canvas also, okay? So hopefully that's useful for you guys to study. All right. So we've been dealing with circuit analysis this chapter. We're going to come back to it, I think, in chapter 30 and also 32. So there'll be like little sprinkles of circuits analysis. And so it is a substantial portion of the class. And the next thing we're going to talk about is this section called getting grounded. So you guys might probably seen this in your lab class across the hall, right? There's these little boxes that they're called voltage power supplies, right? Where you plug in your little thing here and then it gives you a certain voltage. It's basically like a battery, right? But a little bit fancier so that you don't have to deal with this internal resistance thing we talked about last time, and so you can draw more current out of it, right? But when you plug this in, usually this replaces here, right? So basically what you're doing is you're plugging this end over here. I'm going to do a black cable, and you're plugging this end over here, and you're running some resistors here, okay? So some of you guys might have noticed there's this third thing here, okay, called ground, okay? So what the heck is ground? Well, it's not, they don't even tell you it's ground. They just, the symbol is GND, right? And GND stands for ground, okay? Okay? Ground. And you can imagine what that means. We actually see this all the time. Whenever you see outlets, there's always this third prong, right? Even on the power supply for your computer or something like that, there's always this third prong. And people call it the ground prong, right? Or the ground plug, right? So what is that? Okay? So the thing we did in our circuit analysis so far, right? I always tell you that you can declare one point on your circuit to have a potential equals 0. Right? That's one of the things, right? Even back when we were in physics 1, right? When we're doing potential energy, you can declare, I declare that the ground floor here has 0 potential gravitational potential energy, or I can declare that the third floor, on Naragi, has 0 potential energy, and all the equations still works out, right? Hopefully that you guys have seen that. So same thing on a circuit. You can declare any point on a circuit to have 0 voltage. This is useful in theory, okay, when you're just dealing with stuff on a piece of paper or on a whiteboard. But in reality, okay, we actually do need to define one place to have 0 voltage. And this is defining the ground, okay? So let me give you an example here. Oops, right, let's say we have this circuit here. Let's erase that. Okay. Okay. We have this, 3 resistor circuit up here, right? And I say that, well, I can define this spot to be V equal to 0, right? As I go around this loop, what's going to happen is that V is going to be equal to -9 here, okay? All the math will still work out this way, okay? But if I was to install this somewhere, oops, V equals to -9 volt. If I was to install this somewhere with a power supply connecting to this side, right, V equals 0 will actually be physically connected to the ground, meaning, and usually it's like a little symbol like this with 3 lines that's shorter and shorter. What they do is they take a cable and they basically stick it into the ground, okay? If you did that, what's going to happen is that this is going to try to provide a 9-volt voltage here, and all of that current is going to go to ground, and you're basically not powering your device at all, okay? So in this case, we do need to, you don't get to pick it yourself, we do need to pick, right, the bottom down here to be V equal to 0. And if that's V equal to 0, if you do Kirchhoff's voltage law, right, up here it will be 9 volts instead, okay? And when you do that on a circuit, what you do is you basically tell the person who's building the circuit for you, I'm connecting this part of the circuit all to ground, okay? And therefore, when I connect the 9-volt here, all of this 9-volt potential is going to have to go through the circuit in order to get to ground, okay? Why do we have to go to ground? It's more for a safety issue, okay? So in case there's some sort of malfunction in your circuit, right? Let's say your laptop, right? This laptop is actually not connected to ground. I can tell because the plug here is actually only has 2 prongs, has no ground plug, right? But a lot of the maybe bigger computer, the desktop here, right, is connected to ground, has more power running through it, okay? Therefore, it's actually a safety issue where you, in case your computer is malfunctioning and it's, like maybe like the processor is melting or something like that, you overclocked it, right? Or let's not talk about Samsung cell phones anymore. That's old news. But let's say you have some sort of lighting fixture also that's 120 volts, right? You want that to be grounded because in case there's a short circuit, you want all of that energy to go somewhere, right? Just as like a dump, okay? It's a way to route that power so it doesn't stay on your circuit and melt the entire thing so that it actually goes to ground, okay? So this escape route, basically think of that ground as a kind of an escape route for the energy, right? We're going to connect that to the biggest charge reservoir that's available to us, and that's actually the place we're standing on Earth, right? So the planet is, a big, it's a okay conductor, so a lot of charges actually kind of move around. So what we can do if we stick our ground prong to Earth, any excess charges, right, that builds up will go through this ground prong and basically go to Earth, okay? So all of that extra energy just gets dumped in case of a malfunction, okay? And that's why in circuit diagrams, instead of having, this is known as a floating ground, where you can pick anywhere to be 0, what they do is they actually declare this particular part of the circuit to be ground, and therefore you know exactly where 0 volt is, okay? So basically the designer of the circuit picked that place, so it's for a safety issue. So in case there's some sort of malfunction on this simple circuit, all of the current has a place to escape, okay? So let's see, we've got about 15 more minutes. I think I'm not going to go through these examples because hopefully now that you believe me that, if I declared this part to be 0 volts and this part to be basically negative EMF, if you do Kirchhoff's loop law and all that stuff, you're going to end up with the same amount of current running through it, right? As if you would if you declared this to be 0 volt and this to be positive voltage, right? It's the same idea of, do I declare the ground floor of Noragi to be 0 potential energy, or do I declare the 3rd floor of Noragi to be my 0 potential energy, okay? But just for the sake of time today. What I want to go through, so whenever you do see a circuit that has this ground symbol to it, you don't get to choose where 0 volt is anymore. That's the only difference, okay? Right. Okay. So what I want to cover is the next section, and I'm going to tell you right ahead, we do need this information for the later chapter, but I'm not going to put this on the midterm for sure, okay? Because this is just like a tiny introduction to more complicated circuit. Instead of just resistor and only capacitor, now we're going to mix the two together and see what happens. And this is known as RC circuit, R for resistor, C for capacitors, okay? And these RC circuits are very useful. For example, if you ever have any lights that blink at a regular interval, right, that's actually using an RC circuit, okay? And you're going to say, wait, how does an RC circuit, make something that blinks at regular interval, okay? For example, on my Brita filter, the little thing on top that tells you when to change the filter, that's actually an RC circuit, okay? Anytime you have in your computer, anytime there's a clock there's a, a little piece of hardware inside your computer that keeps track of time, how many nanoseconds has passed. That's also an RC circuit, and we're going to see how these RC circuits somehow change resistors and capacitors, which has nothing to do with clocks yet, right, into something that's actually kind of a clock. Okay. So we're going to do, I'm going to start off with the simplest RC circuit. It's just one capacitor, one resistor. And I'm going to study what's going to happen to it if, let's say, we have a fully charged capacitor, meaning it's charged to the maximum voltage it has. So some value, we're going to call that, Q naught. Okay. And we have a switch here at t equal to 0. We're going to close the switch. And then what's going to happen? We're going to allow the current to flow through this circuit. And then we'll see what happens. Okay. So it's just some definition. We're going to have this capacitor with capacitance C. Resistor will have resistor value R, right? So initially, the capacitor is fully charged, so we're going to call that Q0 for the initial time. And initially, there's some potential across this, delta V, and that's going to be delta V naught, right? Following the charge to voltage across the capacitor equation, we can solve this equation for V naught, and therefore that's actually the initial charge divided by the capacitance. That's the amount of charge that's going to be there initially. Okay, we'll just make this all zeros, right? Okay, I'm just kind of declaring a lot of stuff, and then when we go across this resistor, we're going to have a drop in potential across the resistor that's going to be equal to I times R, right? So we're doing Ohm's law, right? And we have the capacitor equation. Okay. Okay. What we're going to do next is going to apply Kirchhoff's law, of course, because that's how we analyze circuits, right? So if we start off at this point here, right? Let me zoom out a little bit too big. If I start off this point here, right, and I'm going in this direction, in the clockwise direction around this loop, right? The first thing I'm going to see a capacitor. I don't know what that amount of voltage is, right? But what I'm going to do is I'm just going to write, this is the change in voltage across some capacitor. I don't know what it is, but we'll see, okay? We're going to see that it's a positive change because there's more positive charge here than there is negative, so that's actually polarized. Okay. Next thing we're going to go, right, if this switch is closed, we're going to see that the next thing we'll see is a resistor. Okay. So we're going to have some change in voltage across the resistor, right? The change in voltage across the capacitor, we've solved this little equation here, changing voltage across the capacitor, is just going to be the charge on that capacitor divided by the capacitance, okay? Right? So that's what we're going to plug in here, okay? So we can even write the cap here, right? The voltage change across a resistor obeys Ohm's law, which is I times R, right? But we are obeying that this is the direction of the current, okay? If we're following the same direction of the current, we actually go downhill, right, across the resistor. So we lose potential here, so therefore that's why we have a negative sign here, okay? You guys see how I got from the diagram to this equation? So this is usually the hardest part, okay? Once we have the equation, right, we can do a lot of math, right? Okay, any questions so far? All right, so now we have this equation, right? We end up at the same point, therefore we can set that equal to 0, okay? So what this is saying is that the charge divided by the capacitance equals to the current times the resistance, okay? And here, what I did, the only difference is I put in explicitly the time dependence, okay? Why is there a time dependence? The reason there's a time dependence is that as these charges leave this capacitor, go through this resistor, and come back here, it's going to meet these negative charge, and they're going to neutralize each other, right? So as time goes on, there's going to be less and less and less and less charge on that capacitor, okay? So the amount of charge is decreasing. So therefore, this charge is decreasing, and therefore, the amount of current that will go through that circuit will also decrease, So there's one more little relationship that we have to figure out, is that this is the amount of current flowing through a resistor, right? Okay, that's the amount of current in that circuit, okay? The amount of current flowing through that circuit is how much charge, right, is moving per time, right? So therefore, we can actually replace this little current as the negative of the charge. The negative sign indicates that the amount of charge is decreasing, right? And we know that just from analyzing the picture, okay? So therefore, we can replace this with negative dq over dt. So if we did that, we end up with this equation here, okay? And now we're in a little bit of trouble. We have some differential, right? We have q here, we have r's here, a bunch of constants. I don't know how to deal with this, right? I mean, so this is where we have a little bit of a strategy that's been used in math over and over and over again. What we're going to do is we're going to take everything that has to do with q, we're going to move it to the left-hand side. Everything that has to do with t, move it to the right-hand side. Those of you who had taken a differential equation class, this is called separation of variable. But you don't need to know that. I'm just going to do some integral here, and that's it. Okay? So solving this equation, well, not solving, massaging this equation, if I move this stuff to the right-hand side, I have a q here, right, with a negative sign because I just moved it to the right, okay? Then what I'm going to do is I'm going to multiply this side by, divide this side by q. So let me just do the math, okay? So if I divide both sides by q, which depends on time, right, and I also divide both sides by r, and then I multiply both sides by t, okay? I'm doing the same thing to both sides, right? This will cancel out, right? And this will cancel out, and this will cancel out. And then what happens is that you end up with just a q on the bottom here, and then dt over rc with a negative sign in front here, okay? That's just me moving some algebra stuff around, okay? Now this is nice because anything that depends on q is on the left-hand side. Anything that depends on time, right? There's no variable here, right? It's just a dt, right? But there's a constant here that we can integrate, okay? If we integrate both sides, okay, the integral of 1 over q is a natural log. You guys remember that from Calc 2? Or you guys do that in Calc 2 or Calc 1? Calc 2, yeah. So that's the special function, right? If you integrate 1 over q, you get natural log. And we're evaluating this from the initial amount of charge to some amount of charge sometime later. Okay, we don't know what that time is yet. Okay, if you evaluate this, you get natural log of big, the q as a function of time, and then the initial charge on it. Okay. One more little additional math thing that you may not have remembered, right? If you subtract two natural log function or any log function, it's actually the same thing as dividing those two log functions. Okay, it's just a properties of log. Okay, so any log function, log a minus log b, it's the same thing as log of a over b. Okay. All right. The right-hand side is pretty simple because we're just integrating a constant, right? If you integrate a constant and you evaluate from 0 to t, you just have that variable, right? Okay. And the constant is 1 over RC, so that 1 over RC is still there. Okay. Now what we can do to solve this equation is by exponentiating both sides. Okay, so remember doing this maybe in like trigonometry or something like that, or college algebra, right? So they are anti-functions of each other, so the natural log and the exponential actually cancel each other. So what you end up on the right over here is q over q naught. The right-hand side doesn't have the natural log, so they don't cancel each other. So you have exponential minus t over rc here. What you can do is move this q naught over here, and then you end up with the equation to figure out how much charge there is on the capacitor as a function of q naught, which is the initial amount of charge, e to the minus t, which is some exponential decay that has some time constant RC. And this is the connection between RC circuits and time, okay? So why is that? So this is a special number because whenever you have an exponential, negative like x over L or something like that, this is actually what's known as the constant of that exponential decay, okay? Because it's constant, it's not a variable, okay? In this case, what we're going to do is we're going to write this equation as Q naught, right, e to the t minus tau, okay? Or this is the Greek letter tau, okay? I think we had a little tau situation back in the mean lifetime, the drift electrons, but this is another tau, which is a different tau, unfortunately. And we're going to define that this tau is going to be, well, we can actually see what it's supposed to be, is R times C. Okay. So this was really wonky to me, right? Resistance times capacitor gives you a quantity that has a unit of time. Is that true? Let's check, right? Let's do our unit, go back to chapter 1 of general physics and do our unit analysis check, right? So resistance times capacitor, the units for resistance is ohm. The unit for capacitance is farad, okay? So the units for ohm is pretty easy to figure out because, right, using Ohm's law, right, change in voltage across a resistor is I times R, right? So therefore, you can solve this equation for R, delta V over I. So therefore, the units for resistance, this ohm is actually the same thing as a voltage per amp, right? Because this is a voltage and this is an amp, right? Farad, we do the other equation, Q equals to change in voltage across the capacitor times the capacitance, right? We solve this equation for C, right? This will be Q over delta V, right? So this will be units of Coulomb. Unfortunately, there's a bunch of C's around, so I'm trying to write the shorthand version of it. Coulomb, okay? And then, of course, delta V is going to have units of voltage. So this will have units of Coulomb per volts. These actually cancel each other out, right? And now we have Coulomb per amp. And what is an amp, though? Amp is a charge per time, right? This is charge per second, Coulomb per second, right? So therefore, right, even the Coulomb cancels out, right? And you have 1 over second in the denominator, and anything in the denominator of a denominator goes in the numerator. So this actually ends up with units of seconds. It's crazy, right? You take ohm, you times the farad, you get seconds. Okay? So in the last couple of minutes here, I just want to show you guys what you can do to basically, you start off with the charge equation. You can actually derive the voltage equation for it and also the current equation, okay? Because, right, the charge on the capacitor is the voltage across that capacitor times the capacitance, right? So if I take this equation, right, and I divide by C, right, then I would actually get the voltage, okay? So the change in voltage across the capacitor is just whatever the charge is on that capacitor divided by the capacitance, not the unit, the variable capacitance. So therefore, if you want to figure out the voltage across that capacitor, it's just Q naught divided by C, right, e to the minus t over tau. What we can do is actually also, we found out that, go back up here, right, the initial voltage, right, is actually exactly Q naught over C. So we can actually replace that Q naught over C with V naught, right? The initial voltage, oops, so the voltage across the capacitor is going to be whatever that initial voltage is. Let's say it's 10 volts. It's going to decay over time exponentially, okay? And the other thing you can do is you can also solve for current, right? The current across that capacitor is just going to be whatever the initial voltage across that capacitor divided by R times the exponential. So it's the same So this is kind of like the time dependent, the behavior. The other part is just the constant, okay? So what you can do is actually you can plot these, and these functions is useful to just see what they look like, right? So if you plot charge versus time, you're going to have an exponential decay, and this tau tells you exactly where it will fall off, how fast it will fall off to about 37% of the initial amount of charge, okay? Same thing with current, right? Current falls off, and then the tau amount of time, meaning this is equal to R times C, it tells you how long it takes for it to discharge to its 30% level. All right, so that's all I have to cover for this section. And just to remind you, there is a couple of homework